The properties, synthesis, and reactions of carboxylic acids is what we're talking about in this lesson. And we'll quickly review a couple properties, both acidity and boiling point. Not going to spend a ton of time there. We will go and take a look at the synthesis of carboxylic acids. We'll see a handful of reactions that you've studied in the past. We'll see a couple of new ones as well. And then we'll go through a handful of the reactions of carboxylic acids, much of which will be review from earlier in this chapter. Now, this lesson is part of my organic chemistry playlist. I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post a new lesson, subscribe to the channel, click the bell notification. All right, so carboxylic acids, just want to remind you that they are acids, hence the name of the functional group, and typical pKa's are in the 4 to 5 range for like acetic acid or something along those lines, and but we've seen those before. What's new though is I want to talk about the boiling point real quick, and take a look at comparing a ketone and an alcohol. You go from 49 degrees for the boiling point here for acetone up to 1 propanol here at 97 degrees, and that's due to hydrogen bonding. So, and a 3 carbon corresponding carboxylic acid though, you see another big jump. They both only have 1 OH, and you might think, well, they have similar amounts of hydrogen bonding. They shouldn't be too different. I mean, a little bit larger with 1 more oxygen and stuff, but it's another significant jump in boiling point. And the reason it comes out, the fact that due to hydrogen bonding here, so they can line up to hydrogen bond between the oxygen hydrogen in one pair and another here as well. So 2 sets of hydrogen bonds occurring between 1 pair of molecules. And so these dimerize, it turns out. And as a result, they appear to be twice as large as they actually are. And that increase in apparent size gives them greater overall London dispersion forces, greater overall intermolecular forces, leading to a higher boiling point than we might have otherwise predicted. So now we're going to take a look at the synthesis of carboxylic acids, and the first few reactions are going to be total review, and we'll start with ozonolysis, both of alkenes as well as alkynes. Now, if you're doing it of alkenes, so both of these lead to oxidative cleavage. So with an alkene, though, you've got 2 options for conditions, both reducing conditions or oxidizing conditions. And under reducing conditions, you produce aldehydes and ketones, whereas on oxidizing conditions, you can produce carboxylic acids and ketones. And so if the goal is to make a carboxylic acid, we want to do this under oxidizing conditions, which we carry out with step 2 using hydrogen peroxide. Reducing conditions, we might have used like dimethyl sulfide or zinc and water, but if we use hydrogen peroxide in step 2, that's ozonolysis under oxidizing conditions. We can also do the same oxidative cleavage reaction with hot concentrated KMNO4 though as well. So, but we'll cleave that alkene. So depending on how substituted it is on either side, you might get a ketone like we will from the left-hand side, but on the right-hand side, it looks like we'd get an aldehyde. And under reducing conditions, that aldehyde would stay an aldehyde. But under oxidizing conditions, it gets further oxidized from an aldehyde to a carboxylic acid as your final product. And so notice both your products aren't necessarily going to be carboxylic acids. They could be depending on what alkene you start with. But if you get a ketone on one side, it's going to be a ketone no matter what the conditions. It's the other side here in this example where we could have got an aldehyde under reducing conditions or a carboxylic acid under oxidizing conditions. Now with an alkyne here, we just got 1 set of conditions here. So here ozone followed by either water or H3O+, and you're going to do oxidative cleavage again. And for an internal alkyne, you're just going to get 2 carboxylic acids. If this thing were symmetrical, it would just be 2 equivalents of the same carboxylic acid. But in this case, it'll be 2 different carboxylic acids being asymmetric. And we got 2 carbons on this side. So that's a 2 carbon carboxylic acid. And here we got 1, 2, 3, 4 carbons on this side. So there's 1, 2, 3, 4 carbons, and there's our 2 carboxylic acids. Now, one thing to note, if you did this with a terminal alkyne, keep in mind that the carbon at the terminus would end up as carbon dioxide instead, which obviously is not a carboxylic acid, but just a reminder of the reaction here. Cool, so that's ozonolysis of alkenes and alkynes. Let's look at another set of review reactions, oxidation of alcohols. Okay, so let's take a look at the oxidation of primary alcohols. And you might recall from the alcohol chapter that with a primary alcohol, you've got 2 different reagents that you can use to oxidize it. Your stronger reagent's chromic acid, and here sodium dichromate in a strong acid like H2SO4 is one way of writing that chromic acid. Or you could use PCC, the weaker reagent, and there's a difference. With the primary alcohol, you are going to oxidize this 2 steps all the way as far as it'll go to a carboxylic acid. So, but with PCC, you would stop, only oxidize it 1 step and get an aldehyde. Well, if we're doing the synthesis of carboxylic acids here, well, then we don't want to consider this reaction for this lesson. So if you want to produce a carboxylic acid, you've got to use chromic acid, not PCC. And as a reminder, chromic acid is going to take your primary alcohol, and it will first convert it into an aldehyde, but then further convert that aldehyde into your carboxylic acid. And so the other reaction that'll get you there then is, well, what if you had the aldehyde to start with? Well, you can oxidize that aldehyde to the carboxylic acid using chromic acid. And another way to write chromic acid, H2CrO4. Just want to remind you of the different ways we represent chromic acid. But it turns out you learned another way to pull this exact reaction off recently as well. And so you can turn an aldehyde into a carboxylic acid in one other way, and that's with the Baeyer-Villiger oxidation. So, and this is really a minor point here, so because we really more predominantly like to think of the Baeyer-Villiger as converting ketones into esters on the more substituted side, but technically it will also convert an aldehyde to a carboxylic acid. And you might recall that the reagent is a peroxy acid. And again, most famous peroxy acid that you commonly see used here is MCPBA. So whether we generically write peroxy acid or specifically write MCPBA, that would be another way to accomplish this. Now you're definitely going to see chromic acid more often in this context, and like I said, we don't like to think of the Baeyer-Villiger as converting aldehydes into carboxylic acids first and foremost. It's kind of like an afterthought. It was really about ketones into esters, but it will do this, so we'll bring it up here very briefly. All right, the last review way of making a carboxylic acid before we cover a couple of new ones was side chain oxidation. We learned in the reaction of aromatic compounds chapter. And in this case, with side chain oxidation, we learned that we can oxidize the benzylic carbon with hot potassium permanganate and just acidify it to protonate the carboxylic acids. Turns out you can also do it with chromic acid. Turns out I didn't cover it at the time, but some classes will see it either way. In this case, it's your benzylic carbon that gets oxidized. And so if all you have is a benzylic carbon like we do on this side, that becomes a carboxylic acid. So, but it turns out if you have more than just a benzylic carbon, one carbon away from the benzene ring itself, you'll cleave off all the rest of them and still oxidize that one remaining carbon to a carboxylic acid. And yet another way we learned how to synthesize carboxylic acids. Now, one thing to note, and we covered it back in the day, but if your benzylic carbon does not have any hydrogens, if it's quaternary, then the reaction's not going to occur there. Just a reminder. Cool. And again, that concludes our review methods, our old methods we've already learned previously for making carboxylic acids. Let's go look at those new ones. Okay, so what we have not covered as a way of making a carboxylic acid is something that we talked about with the nucleophilic acyl substitution lesson, is that with any carboxylic acid derivative, and we said whether it's an acid chloride, an anhydride, an ester, or an amide, any of them, you add H3O+, and in the case of the amide, H3O+ and heat, they all convert into carboxylic acids. So that's old. What we didn't necessarily explicitly mention, or at least not make a big point of at the time, was that nitriles, also being a carboxylic acid derivative, if you add H3O+ to them, you will also get the carboxylic acid. And so we can really make that overall point that any carboxylic acid derivative, you add H3O+, you are going to get a carboxylic acid. So you can kind of see how the mechanism goes here and stuff like that. So you actually use the H3O+ to protonate the nitrogen, and then a water molecule's kind of come and do nucleophilic attack on this carbon, push these electrons out. You'll deprotonate the oxygen, protonate the nitrogen. You'll keep protonating the nitrogen until it's a good leaving group of leaves. You'll keep deprotonating the oxygen until it's going to stay, and then you'll bring another water molecule into a denucleophilic attack as well, finally getting your carboxylic acid. So I'm not covering the mechanism explicitly, and a few of you will be on the hook for it, but I'm not going to take the time to cover it. My apologies. But just want to show you one further way that's new for making a carboxylic acid. Let's look at one more. All right, so our last method of making a carboxylic acid, and once again new, is going to involve a Grignard. Now, we originally learned Grignards in the context of nucleophilic addition to ketones and aldehydes, and then we saw in this chapter they can also be used for nucleophilic substitution / addition. Addition of two equivalents for acid halides and hydrides and esters. Well, key is they were reacting with a carbon-oxygen double bond in any case. So and you're just going to come and do nucleophilic attack on the carbon-oxygen double bond, push those electrons up. So, and if this were a ketone or aldehyde, you'd be making an alcohol. If this had a leaving group, because it's an acid, halide, anhydride, or ester, you'd be doing nucleophilic substitution, producing a ketone, and then the ketone react. Well, what if instead of having, you know, a normal carbonyl, what if this had been part of a carbon that's double bonded to yet another oxygen, i.e. carbon dioxide? So, but the same thing is going to happen here, it turns out. So, still going to do nucleophilic attack. We're still going to have one carbon oxygen double bond, but now this one's going to be a single bond to the other oxygen and have a negative charge. And so what you do is you do Grignard addition to carbon dioxide first, and then just like any Grignard, you follow it up with an acid workup step to protonate that and make your corresponding carboxylic acid. Now here I did it with a phenyl magnesium bromide, a phenyl Grignard, but again, any Grignard will work with this. You could have used a methyl Grignard and made, ethanoic acid. Here I just used a phenyl Grignard and made benzoic acid. Cool, but Grignard addition to CO2, last thing we've looked at with a Grignard. So with a Grignard, we learned how to attack either formaldehyde and aldehyde or a ketone to make either primary, secondary, or tertiary alcohols. We've learned how to attack earlier in this chapter acid halides and hydrides or esters with two equivalents to make a tertiary alcohol. And now we've learned that we can do Grignard addition to carbon dioxide to make a carboxylic acid. So now we want to take a look at the reactions of carboxylic acids, and this is pretty much going to be all review. Now, a bulk of the reactions are all tied up again in this interconversion chart from Nucleophilic Acyl Substitution lesson. And if we look at, starting with a carboxylic acid, what can you do with it? Well, we can turn it into one of the corresponding acyl halides, either an acid chloride or an acid bromide using SOCl2 or PBr3. And we've now brought that up a couple of times throughout this chapter, so that's not new. But what else can we turn that carboxylic acid in? Well, we can turn that carboxylic acid into the corresponding ester. And if you recall, if you're starting with that carboxylic acid, you can't do the base catalyzed reaction. So the only option we have is the acid catalyzed reaction. So using the appropriate alcohol and the appropriate, or just any acid catalyst. And if you recall, that was called Fischer Esterification. So we saw it when we talked about the synthesis of esters, but it's also a reaction of carboxylic acids. So a lot of these reactions showing up in multiple places, and just, again, how you properly need to organize them in your head. Now we can also make an amide here, it turns out, from the carboxylic acid. It is lower in reactivity. And once again, you've got to do it with acid catalysis. And I don't formally have a great place to show that, do I? Well, technically, you just need to do the acid catalyzed version of this, and you can use the appropriate amine and acid catalyst. And again, technically, I should have found some way to incorporate that on the chart here, though I didn't. But that's going to be the case there. And then finally, obviously, you can just simply do an acid-base reaction. Add a strong base, hydroxide, you can form the corresponding conjugate base, a carboxylate ion. Cool, and that's what's old from the nucleophilic acyl substitution. We've also got some hydride reductions that we studied a couple lessons ago as well. So now we'll take a look at hydride reduction. And once again, recall that for the acid halide, the anhydride or ketones or aldehydes, sodium borohydride and lithium aluminum hydride both work. But for anything less reactive, starting from here on down, including the carboxylic acid, you can't use sodium borohydride. So we've got to use lithium aluminum hydride here. And the mechanism here is a little bit funky, so I'm not actually going to cover it. Most of you aren't going to be on the hook for it. But we'll reduce this all the way down to a primary alcohol, but it's not through the normal, standard nucleophilic acyl substitution method we're used to seeing. So I'm not going to actually represent it as such and stuff. But you might have thought, oh yeah, we're going to place the OH with an H and get an aldehyde, and then add another H, and so on and so forth. It actually is more complicated than that. But again, most of you aren't on the hook for it, so I'm not going to cover it here. And one alternative, though, is not sodium borohydride, but borane here. And it turns out for a carboxylic acid, borane will actually accomplish the same process. So once again, I'm not going to cover the mechanism on this one. In fact, I would say probably at least 3/4 of you probably aren't going to see this as part of your curriculum. But for the other 20-25% of you, I included it just for you. But again, if you haven't seen this borane used in this context, then by all means just ignore this reaction. Now, if you found this lesson helpful, would you consider giving me a like and a share? Best thing you can do to make sure that other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on carboxylic acids and their derivatives, check out my premium course at chadsprep.com.